Welcome AP Mechanics students. Today's review topic is gravitation. As you could see from this list, we've got a lot of things to go over today. Force, gravitational field of a planet, gravitational potential energy, space projectiles, circular orbits, elliptical orbits, and Kepler's 3 laws. Because we have so much to cover, and as I've said all along through these review videos, we don't want to go over every single detail. I'm going to be giving you just the main ideas, and then I'm going to show some kinds of example problems, and within those example problems, when possible, I will try and avoid as much detail as possible and just show you the overall pattern, the thoughts that go into, and the setup that goes into solving the problems. Okay, so that's what's coming. All right, so let's begin. So the first topic within gravitation, as you saw in the outline, is force. So any two objects in the universe attract each other. Force of gravity is always an attraction, never a repulsion like with charges or with magnets. So we can put these arrows here. By Newton's third law, the force of attraction is mutual, meaning even if this is one big object like the Earth and this is like a penny, then the attraction between the two, the Earth pulls the penny with a certain number of newtons, the penny pulls right back with the same number of newtons, even though it's very small compared to the Earth, very minuscule. This is, of course, the formula, universal law of gravitation, the constant G, 6.67 times 10 to the minus 11 Newton meters squared over kilogram squared. So this you don't have to memorize, of course, that comes on the table of information that you're given for the AP test. So let me just talk a little bit more about force with a simple example. So I have here 3 objects. Okay, so quarter, penny, and a nickel. So just a reminder, this force of gravity is a vector, so you have to do vector sums when you're figuring out the net force caused by multiple objects. These two attract each other, right? So whether one's bigger or smaller, they attract with a mutual attraction, same length arrows on each other like that. But what if I wanted to find the net force caused on the penny in the middle here? What I would do is I would use the formula I just covered up, GMM over R squared, and figure out the length of this arrow between these two. Okay? Then I would calculate another force between these two, GMM over R squared, and I would get the length of this arrow. Now, I have them the same length, but they might not be the same length. These are in opposite directions, so what I would have to do, like let's say this, I'll make up a number, is 10 newtons and this is 8 newtons. To get the net force on the penny, I would subtract. So with vectors, when you're adding vectors, sometimes you might be subtracting them. Or you might be adding them. Let's suppose I move this quarter over here, then the attraction between the penny and the quarter is now pulling the penny also to the right. So both of these attractions to both these objects are to the right. So now when I find the net force, instead of subtracting, I add these 2 Newton values that I calculate from the formula. Another possibility is maybe I move the quarter over here, and then I have an attraction to the nickel to the right, and attraction to the quarter toward the top of the page. So in that case, I would have to create dotted lines here, a diagonal, and I'd use the Pythagorean theorem. Okay, so vector sum, adding, subtracting, Pythagorean theorem. If you go like this, you might construct a net force like this somewhere and use the law of cosines or law of sines. Okay, so all vector sums. Again, I'm not going to go into those details because they'll change problem to problem. But I just wanted to point out that that is the case with gravitation. Vector sums, not just scalar sums. Okay, so things attract each other. But it turns out that that is not actually an accurate way to say what's going on. What really happens is there's something called a gravitational field. So let's take two objects again, like this. The one object creates a gravitational field pointing toward itself. That's what this diagram is showing. So there's a field G that points everywhere toward that object, and it gets weaker the further you get out from the object. This is a picture, a vector diagram representation of the gravitational field, but you could calculate the gravitational field using this formula. Okay, so this is that constant, this is the mass of object 1, and this is how far away you are. So this would be the length of the arrow at, say, this given distance. You would plug in everything, get the length of the arrow. Now, what does that field do? So I have this object, maybe it's the quarter, creates a gravitational field toward it, and then when I put the penny here, it doesn't directly get attracted to here, it gets indirectly attracted because the attraction is caused by actually the gravitational field. This penny is attracted because there's a field here caused by the quarter. So it's just another step in our thinking. We used to say they attract each other with this formula, but more specifically what happens, the way the attraction works, is this object first creates a field in the space around it. So there's an arrow pointing in the direction of the quarter, and then when this finds itself in the field, it experiences this force. Now if you put these two formulas together, you put gm over r squared here, you get gm1m2 over r squared back. So in cases where things aren't accelerating, it's kind of not really necessary to calculate gravitational field, but when there's acceleration and time delays, then in motion, then you do need the gravitational field to more accurately model. But nonetheless, you need to know what it is and how to calculate. All right. Another thing I want to talk about today is the gravitational field within a planet. So what I mean by that is, if you're above the planet, we could just use this formula for the field above the planet. But what happens when you start tunneling in? Now, according to the formula, if you use this blindly, you would say, well, the radius is getting smaller, so the field gets bigger and bigger, and maybe it's an infinite value at the center of the planet. And it turns out that's not true. Because, so let's take a planet of mass m, radius r. So this light line represents the surface of the planet. And you tunnel in and you're here a radius little r from the center of the planet. Okay? So the only part of the planet that creates a net gravitational field is the part of the planet that's at a smaller radius. Just imagine you're here in this tunnel. You've got some part of the Earth pulling you continually towards the center of the Earth, but there's a part above you that's pulling you out toward the surface because it's attracting you this way. So you see that effect is that it cancels itself by canceling, it basically opposes the field here. In fact, the real way to think about this is that any mass that's at a larger radius out here, in the end, the overall effect cancels itself, so there's no effect on the field caused by the mass out here. The only part that causes a net gravitational field is the part at a smaller radius, as I said. So the way to figure out the field inside the Earth is with this formula, but using only the mass inside at a smaller radius than where you are as you're tunneling toward the center of the planet. Now, how do we get the mass in here? It's obviously just a portion of the total mass of the planet. What we do is we use the concept of density. So I don't know what symbol you're familiar with density, but in physics we use the Greek letter rho. Okay, it's a Greek letter just like pi is, or mu, the friction coefficient. This is another Greek letter. It means density. And density, of course, is mass over volume. So if you want the mass, you multiply density times volume. So this is the density of the planet. This is the volume at a smaller radius than where we are in our tunneling. That will give you the mass. So we have gm over r squared, just like the formula up here. Now, we can calculate the density by the definition, density is total mass over total volume. So that's what we have here. The total mass of the planet over the total volume of the planet. The volume of a sphere is 4/3 pi r cubed. Capital R, the whole planet. Now we multiply the volume by the volume of what's inside at a smaller radius. Also 4/3 pi r cubed because it's a sphere, right? But little r because we are at we want the radius of the planet, portion of the planet inside. And that's all over r squared. Gm over r squared. And if you just do simplifying, cross out all the common terms that are in the numerator denominator, you get to here. Okay, so you see the mass of the planet actually at radius 0, the center of the planet, I mean the gravitational field at the center, if you plug in r equals 0, you get 0g, 0 net field in the center of the planet. And it grows radially, I mean linearly, as you tunnel outward. You get more and more field because of the r in the numerator. Once you get outside the planet, then it's just this formula, Gm over r squared. Also, if, by the way, if they tell you the density of the planet, this whole term right here would be just density. And if you touch everything up, you would get this for the final answer of the gravitation, still as a function of r to the 1 power, 0 in the middle, and growing radially outward. We could plot all this in a graph, very common in these problems to plot the pattern. So I create my axes, G, the field here, radius here, the radius of the planet, twice the radius of the planet. I show that the field is 0 at the center of the planet, grows linearly to the outside. Now I always, when I draw graphs, I like to label the mathematical relationship. I put proportional to r, that's what this means. The reason why is because you're drawing this by hand, and my line isn't straight actually. You could see that I was a little bit off in drawing that straight. So what if the person grading this says, oh, that person who took this test thinks that it should be some kind of curve. I'm going to take points off. So by writing this here, you kind of protect yourself from that. Even if you're sloppy drawing, the person grading could say, oh, all right, they're sloppy, they're not the best drawer, we won't punish them for that. They understand that it's a straight line there because they wrote that and they won't take points off. Same here, what if I went fast and it kind of wasn't quite clear that it was a curve? Then I put proportional to 1 over r squared. That tells the grader that it's going down as a curve. Okay, so 3 ideas here. Okay. Force, gravitational field, and the field of a planet inside 0 grow, and then 1 over r squared. What I want to do is just now look at a couple examples of some kinds of calculations you might encounter with force and gravitational field in particular. So, all right. Here's example 1. Okay. Suppose we're asked to find the net gravitational field, and here's the diagram. The net gravitational field at the origin. So we've got 2m here at x equals negative 3d. So here's the x-axis, here's the y-axis. So back here we've got 2m. At a coordinate of y equals negative d, down, we've got 1m. And we want to find the net field here. So remember, gravitational field is an arrow, it's a vector, it's a disturbance in space that points everywhere toward the mass in question. So this mass has a field pointing toward it, everywhere. So at this point, it points directly at this mass. So there I have color coordinated blue, showing the field caused by the 2m mass. This also has a gravitational field pointing toward it everywhere. So at the origin, the field points toward this mass over here. So they're not aligned, so I cannot use addition or subtraction. I've got to use a vector sum, like Pythagorean theorem or something. That's what we're going to see here to find this net field. Field this way, field that way, net goes that way at a certain angle. So this is how I would calculate that field. what I would do is I would calculate the lengths of these arrows using the formula gm over r squared. So this one's easy. It's just m at a distance d, so m at a distance d. Okay. This field here, it's a mass of 2m at a distance of 3d. When you square that, you get 2/9 gm over d squared. To find the net field, we've got to basically use the Pythagorean theorem here, as I said, which is hypotenuse squared equals x squared plus y squared. So to get the hypotenuse, I take the square root. So this is, as I've done before, the emphasis here. Make sure you understand this step. Don't worry necessarily about the details. Maybe this in the AP could be 4m at 2d or something, right? So the actual details, not important. The setup is what you want to focus on today. So when you do the Pythagorean theorem, carefully squaring all these and then adding and taking the square root, I believe, maybe I made a mistake, but I believe you get root 85 over 9 gm over d squared. Okay? Again, this isn't so important, but the thoughts behind the setup are. The angle. So what I need to do is use some kind of trig function. I know this now. This side is the same as g1, and this side is this. So I could use tan theta is opposite over adjacent. That's what I did over here. The opposite side is the length of g1, the green arrow, which is gm over d squared. So that's opposite over adjacent. So this is the adjacent. This here is that, which I put down here. This simplifies when you invert this and multiply to the top, you get 9/2. All the other variables go away. And then so the angle is the inverse tan of 9 over 2. This would probably be like a common, if it came up on a multiple choice, to just leave the answer like that. Of course, you could always punch it into your calculator, get 77 degrees. But a lot of times on multiple choice, they leave answers like that. So there's an example of having to use the Pythagorean theorem, a vector sum, when the two objects are creating fields 90 degrees to each other. Let's take a look at another example. So this was like what I showed in the beginning with the penny, and the penny was in the middle, and we had the quarter and the nickel on the sides, and then we had forces opposing each other. This time what I want to do is find where the net force on little m is 0. Okay, so it's somewhere in the middle. If I put it right here in the middle, little m, this smaller mass would always create a smaller attraction than this bigger mass would create a bigger. So this little m would accelerate to the right. So what I have to do is move it to a place where the force caused by this gets weaker and the force caused by this gets stronger. By sliding this out here, I'm decreasing the radius here, increasing the attraction here, but increasing this denominator, decreasing this attraction. So this right arrow gets smaller, the left arrow gets bigger, until I find a place somewhere here where theoretically it's possible for them to have the same size. And then we got, say, 2 newtons and 2 newtons, or net force 0 right there. So that's what I drew here. 2 arrows of equal attraction here and attraction there equal, that means the F net is 0. So with this being at x equals 0 and this being at x equals d, if this is like an x-axis here, then the radius between these two, because I need gmm over r squared, so I got the masses. What are the radii? So this is just going to be x, a distance x from the origin, x equals 0. That's the radius between these two masses. What's the radius here? Well, if the whole distance is d, and then this is x, then this is d minus x, gives me that. So that's the radius between these two masses. So the basic way to start the calculation is just to say the two forces are equal to each other. And then the net force is 0. So gmm, that's what's here, over r squared. Okay? And then here, gmm over r squared. So that's the important step. When you look this over, make sure you can understand what's happening here. Maybe I'll do it here. In that step, okay? As I said, the rest are details that'll change in a problem if they change the masses and the distances and whatnot. But basically what I did is I canceled all the terms that are constant on both sides, the g's, the capital M's, the lower m's. So all I have is 4 here and 1 here. So I multiply 4 times x squared, right? And then this parenthesis term times 1 over here gives me the other side. Square root both sides, add this, divide, and then you have the answer. Again, these details not so important as understanding where that came from. So there's an example, or a couple example problems of the vector nature of gravitational field and force. Things that are likely to come up, maybe, these look like to me like maybe more multiple choice kind of questions on the AP. Well, we got a lot more topics to go, so let's move on. Okay. So, coming next, gravitational potential energy. Remember, with gravitational potential energy, first of all, any potential energy, you need a conservative force. So, if this is the ground over here on your screen, and this is rising up, so the conservative force means that if I lift this and then I bring it down, the work done by the conservative force is opposite and equal. In other words, the conservative force does say negative 5 joules this way when I lift it up. As I bring it back to its original position, the conservative force now does positive 5 joules. That makes it conservative. Friction is not a conservative force. If I push force times distance and, well, actually friction would go the opposite way. So as I push this way and the friction is this way, friction does negative 5 joules of work. When I push it back, friction is this way, cos 180, friction work is negative 5 again. Negative 5, not opposite. So it's not a conservative force. You cannot have potential energy from friction. So just a little thing that is part of the curriculum, by the way. But in the energy unit, we learned UG was equal to mgh. That's just an approximation. That's only true if your altitude change is not that big. Like if you climbed from the bottom of an Empire State Building to the top of the Empire State Building, the force of gravity is roughly constant the whole distance. That's the key. But when you are lifting something into outer, not just up the Empire State Building, a tiny displacement, but up into outer space, the force of gravity is changing, so we need to calculate the work with an integral. The change in potential energy is the integral of force times distance. This gives me the joules for like a tiny displacement, like a millionth of a meter or something. Then I add up all the force times distances, all the work of the little displacements as I'm rising up. That will be the potential energy change, force times distance integrated. So this integral you're actually responsible for. It's in the curriculum. I would say it's not that important in the sense that it's not that likely to come up, okay? But I'll show you how it's done nonetheless. So the force of gravity, if when we do this dot product, dr is this way and the force of gravity is the opposite way. So that's where this negative comes from. When you do this dot product, the angle between force and dr is 180 degrees. F dr cos 180 gives us that negative sign. This is gmm over r squared. I write it this way to help me with the integration. And the dr is still there. Minuses go away. Oh, and by the way, I skipped ahead. I'm kind of rushing here. The limits are critical. Why do we start from infinity and integrate inward? The reason for that is that when things are moving around from one planet to another, or maybe even one solar system or one galaxy to another, the surface of the Earth becomes kind of meaningless when you're flying all the way across the universe. So that's where we always, in our problems, when we were doing energy, we called this potential energy zero. Again, for something moving around on another planet, Earth's surface, kind of hard to understand the relevance. So what physicists have done when things move on an interplanetary scale is they set potential energy equal to zero at some place in outer space that's far away from all masses. And what that means then is that potential energy is zero at that point. All potential energies are going to be negative because we fall into the planet. We decrease potential energy, we increase potential energy. If we start at zero and then we decrease from there, we're going to get negative potential energies. But nonetheless, we'll see that come out mathematically. This is how the details show. From infinity in, that's just potential energy. And then when we integrate, we add 1 to the exponent, giving us -1. Divide by that new exponent. That gives us the minus sign back. And then we plug in our limits. 1 over r, 1 over infinity, that's 0, giving us our potential energy. Now, sometimes this confuses people. So this is a graph of potential energy, always negative, never positive, okay? Starts at 0, gets more and more negative as you come toward a planet, decreasing your radius. So let's suppose we're standing on the surface of the Earth, distance d from the center of the Earth, and I'm just going to make up a number that our potential energy is -10. It's much greater than that. It might be like a million, -1 million, but I don't know. I didn't calculate it out, but I'm making up a number just so we could kind of deal with concepts. Now I go from the surface of the Earth and I go way into outer space at 5 times the radius from the Earth. And then I calculate my potential energy. I see it's -2. Some people will say that decreased. We went from -10 to -2. That's a decrease because 10 is bigger than 2. That is not a decrease. A -10 to a -2 is actually an increase of 8. So don't look at the numbers. It kind of flips things around. The more negative it is, the smaller the number is. Okay? All right, so that's potential energy. Like I said, you have to be able to do this, but don't put too much energy into memorizing this because it comes up not as often as other things. Let's move on. Space projectiles. What I mean is something that's launched and it doesn't just move from one side of a classroom to another like tiny Earth projectile. We're shooting something and it goes way out of the atmosphere, past the International Space Station, or way out here and maybe falls back in, or maybe does not. Maybe we send a probe to another galaxy and it just goes back up and never comes back. All possibilities with space projectiles. Things don't always fall back to the Earth. If you shoot it fast enough, it goes out, never comes back. 3 cases here. One is where we have a relatively small kinetic energy, bigger and very large kinetic energy. So let's suppose case 1, I calculate the potential energy of an object on the surface of the Earth, I get -10. And then I shoot this object up with a kinetic energy that's less than 10, like 4, less than the absolute value of the potential. That makes my mechanical energy less than 0. 4 plus -10 gives me -6. So that's what's going on here. I'm shooting this up and it has a mechanical energy that's negative. I use energy conservation to analyze this. In the beginning, I have kinetic energy because I've shot this up with a velocity, and I have potential energy because I'm not at infinity. This goes up, goes up, goes up, slows down and stops somewhere in outer space, and then it's going to fall back to the Earth. How high does it go? We could figure that out by setting the energy before equal to the energy after. No kinetic here, right? Because it's reached its maximum height. So, kinetic energy in the beginning, gravitational energy in the beginning. I use capital R, the radius of the planet I'm launching, maybe it's Earth. And potential energy over here. What I have here is everything known except for a formula that relates the speed I launch with the radius final, how high it goes. Notice the mass of the thing I'm launching drops out. So whether I'm launching a penny up or a big giant rocket, it'll reach the same altitude. That's true of when we were studying things on just projectiles earlier in the year. So I could figure out how high this went. The faster I shoot it, the bigger R gets. Okay? So that's case 1, mechanical energy negative. Case 2, let's suppose I shoot it even faster. Instead of a kinetic energy of 4, I shoot with 10, which is equal to the absolute value of the gravitational potential energy on the surface. That makes the mechanical energy 0. That's the key here. 10 plus negative 10 is 0. Not negative mechanical energy, but 0 mechanical energy. What we find in this case is this is the speed at which this will go way into outer space and get to an infinite distance with 0 kinetic energy and 0 potential energy out there. And out here, it's escaped. Why? Because if we are an infinite distance from planet Earth, that means force of gravity is 0. It'll never get pulled back in. Here, the force of gravity is not 0, so it accelerates back and falls to the Earth. Here, it does not. We reach deep outer space, far enough from Earth, it will never come back. So the way we figure out how fast to shoot for such an escape to occur is we set energy before, kinetic plus gravitation, equal to energy after, which is 0. Energy, kinetic, gravitation before equals 0. You could solve this for the escape speed from a particular planet. This is the mass of the planet, and that's the radius of the planet, not the mass of the projectile. Remember when we studied this in class earlier in the year? We figured out the escape speed for Earth. It was like 11,000, I think, 290 meters per second, which is extremely fast. Maybe that's like 8 miles a second or so. 8 miles per second, right? That's extremely fast. Thousands of miles an hour. Shoot it up and it never comes back. Escape speed. The third case, instead of kinetic energy being just equal to the absolute value of gravitation, what if it's even greater than that? Well, then that's the case where you shoot more than enough to greater than 11,290, and when it gets to outer space, it'll have kinetic energy left over to keep going. It'll have velocity still instead of coming to a rest out there. So what we do, we realize, first of all, the mechanical energy is now positive. Negative, 0, now positive mechanical energy. 12 plus negative 10 is positive 2, greater than 0. What we could do is figure out the final speed in outer space when it gets way out here from energy conservation. We have potential and gravitational before. Potential and kinetic before. Kinetic, potential. And then we have just kinetic out here. And so what we have is a formula between initial and final speed. We could figure out, say, instead of 11,290, 15,000 meters per second launched here. How fast is it moving when it's escaped Earth? And we calculate, we get some speed there. By the way, as I mentioned when we studied this, the motion is symmetric. In other words, if I'll make up a number, I find out that I have 15,000, for 15,000 meters per second here, I end up with 6,000 meters per second here or something like that. I don't know, whatever it is. If something, instead of starting here with 15,000 and ending with 6,000, what if it starts with 6,000 and it's targeted toward the Earth? All we do is change this to initial and final, but the numbers stay the same. 6,000 and it'll hit with 15,000. We saw that when we launched something from the ground, and I said if I launch it up at 7 meters per second, it comes and strikes at 7. Same thing here. Same thing here. If something starts at rest and falls into the Earth, it'll hit with 11,290. Okay? Space projectiles, 3 different cases. All right. Probably a little bit more common, well, not a little bit, but definitely more common, more likely to be on the AP are orbits and analyzing orbits. So space projectiles, if it's too much, like I said, don't concentrate. Concentrate on this. This is very likely in terms of gravity problems. Most likely thing is the stuff I'm about to show you, probably in my estimation. So first thing, circular orbit. We've got some planet, or maybe this is the sun. The bigger object, I use capital M, and something is orbiting that. Maybe if it's the Earth, we got a satellite, like a communication satellite orbiting, so a little m. Or if this is the sun, giant mass, maybe this is like the mass of the Earth, a smaller mass orbiting. What you have to realize, like anything in circular motion, whether you spin something on a string or go around a corner in your car, you always need a force toward the center of the orbit. And in the case of something satellite orbiting or planet, it's the force of gravity creating that centripetal force. So the first place I start is right here. But I want to point out, this equation does not say that there are two forces that are equal and in equilibrium. In equilibrium, this will go in a straight line. There is only one force. It's causing an acceleration, a centripetal acceleration. This equation says in order to go in circular motion, we need a centripetal force. It could be tension, it could be force of friction, normal force. It could be anything, but we need a centripetal force. In this particular case, it's the force of gravity. It's equal to what we need, so we have circular motion. This is the only one force, and it's equal to what's required to create a circle. That's really what the formula is saying. You could also say that we need a centripetal acceleration, and that's caused by the gravitational field. So you could start the calculation here also. In general, the centripetal force is mv squared over r. So then, and the gravitational force is in general this. So cancel out the mass, solve for v, there it is. By the way, you can't start here. A lot of students, when they're asked a question on the AP, they'll just say, oh, v is radical, and they plug in the numbers. If you're asked for the speed of something, you have to derive this and show that you know how to derive it. In the AP, remember, if you look at the answer keys, most of the points are in the step before. This is like 1 point, okay? So if this is a 4-point problem, 3 out of the 4 points are here. This is only 1 point, okay? So the work is more important than the answer. I've been saying that all along. All right, so that's how fast the speed required to keep that circular orbit. What about the period or the time of orbit? Well, we take this and we set it equal to distance over time and solve for time. The distance around a circle, circumference, 2 pi r, and capital T we use for period, like in simple harmonic motion instead of lowercase t. So what I did is square both sides and I solve for t squared and I get this. Okay, now in order to get the time, I need to take a square root of both sides. But I left it in this form because this is the form that it captures another thing we're going to talk about later, Kepler's third law, and you need to be able to derive this. Starting here, boom, 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 to here. That's part of the curriculum. Okay, so that's why I left it in that form. So we could plug in the radius of orbit and mass of the thing you're orbiting and figure out the time it takes to go around the planet once. Moving on, the energy of an orbit. So we have kinetic and gravitational when we're orbiting up here. The kinetic, 1/2 mv squared, we take this, plug it in, and then gravitational potential energy, mm over r. And we simplify carefully, we get to here. Again, I left out some steps because we're looking at the highlights here. And so really what you want to do is, I guess maybe I should do some highlights since I said we're highlighting here. Okay, this step is what you want to focus on here. Maybe this step is the setup, right? The rest is just algebra. And right here, I will say that's the important thing of the essence of the energy in an orbit, how you calculate it, okay? All right, well, let's take a look at an example. I'm just going to do one example with numbers because you'll see numbers in gravitation can get pretty tedious. What we have is a 1,000 kilogram satellite. It began in a circular orbit at a radius of 6.5 10 to the 6. The radius of the Earth is 6.37, so we're like a little bit above the Earth, above the atmosphere. But later it falls into the ocean at 2,000 meters a second, so it spirals in and crashes into the ocean. Determine the orbit speed before the crash, and then the loss of the mechanical energy during the fall. All right, so again, we can't just write this out and start it. You got to derive it and show your work to get the points on the problem. So we begin as before. We need a circular force. It's gravity that creates centripetal force. We plug in what centripetal force is, what gravity force is, and then we go ahead and solve for V. So let me move this over, make room for the next page. Okay. So, oops, got to bring this down a little bit. Okay, so now we solve for V and we get this, V square root, and now we plug in our numbers. This is capital G, right, on the reference sheet. This is the mass of the Earth. I don't think it's on the reference sheet. That would probably have to be given to you within the problem. So it should be written here. You don't have to memorize that. And then the radius of orbit. Punch on the calculator and you get 7,833. Extremely fast. Okay, that's like 5 miles a second maybe. 5 miles per second, right? That's extremely fast. All right, part B, the loss of the mechanical energy. What we have to do, like, first I'm going to calculate the change in mechanical energy, which is, any change is calculated as final minus initial. In the final, when the thing falls into the Earth, it still has kinetic energy because it has velocity. And there's also potential energy because potential energy is always non-zero unless you're in deep outer space. Before in orbit, it had kinetic and potential. So those are the initial. Look at the numbers, how tedious. So this is the final, 1/2 mv squared. It hit the ocean with this. This is the mass of the satellite falling in. Gravitational potential energy, Gmm over r. Okay, final, when it hits the Earth, the radius of the Earth. Again, that would have to be given. I didn't give it in the problem, but I should have. So, point is, don't get nervous. Oh, I got to memorize that. So this is all the final energy minus, right, the initial energy, what it had in outer space when it was orbiting. 1/2 mv squared, the kinetic energy, the speed of orbit, and then Gmm over r potential with 6.5 instead of, because it was up in outer space orbiting. Potential energy, of course, negative. Hit that on the calculator as carefully as you can. Who knows, maybe I pushed the wrong button. Hopefully this is correct. -3 times 10 to the 10th. But the point is, again, if this is wrong, really the AP is going to be giving you credit for something like this. Okay? So if we had a change that's negative, that means we lost that amount. Okay, so a couple examples. All right? Okay. Long video, right? Lots of things. We're up to like 45 minutes or something, 43 minutes. I see 44. Okay. So that's what we just did. But we're almost there. Okay. So we studied just now circular orbits, but the truth is most orbits are elliptical. Even things that look circular are slightly elliptical. Most things. There's very few things that are perfectly circular orbits. So here's a couple ways to analyze elliptical orbits. Energy or angular momentum. First we're going to look at energy. So what I have in the picture here is a planet or the thing in the middle that's being orbiting. Maybe this is the sun and this is like Halley's Comet, smaller mass, orbiting around like this once every 80 something years, whatever it is. So in position A, as this is orbiting around, it has kinetic energy and potential energy. And in position B, it has kinetic energy and potential also. It's moving slower, but the potential energy is greater, so the point is energy is conserved. Even though you lose this on the way out, you gain potential. Totals conserved. So this is big idea here. And then we fill in what kinetic energy is at A, what potential energy is at A, kinetic energy at B, potential at B. Okay? Notice the mass of the thing that's in the orbit. If this is the mass of Halley's Comet, for example, or planet Earth, or whatever, it drops out of the calculation. And what we have is a formula that relates 4 variables. The speed at A and the radius at A, the speed at B and the radius at B. So the calculation would be, they'd give you 3 of these, and they would ask you to solve for the third. So, for example, they might say the Halley's Comet has a speed of this at this particular radius, and then where is the speed, you know, say half that value, and then so you solve for RB. So that's the important setup right there. So maybe I'll put that so you could sort of realize that's the thing you want to focus on, the understanding that goes into creating this expression. But I won't plug in numbers because, as we saw, when it comes to orbits and energies, large, huge, tiny numbers, huge numbers, you know, very tedious calculation. But that's how you set it up. All right, well, another thing that's conserved besides mechanical energy in an orbit is angular momentum. And the reason why is when there's an attraction here, gravity, there is a force, it creates no torque. Because here's the radius, and the force of gravity points directly inward. So maybe radius this way, they're 180 degrees apart from each other. And from the rotational unit, torque is RF sine 180, zero torque, and so the angular momentum stays constant. But energy conservation, you could pick any points along here, and it's just as tedious, no harder, to pick these 2 points or those 2 points. But when it comes to angular momentum, it turns out that using angular momentum being conserved is only convenient when you're at the closest point and the furthest point in the orbit. And the reason why is this has angular momentum even though it's not spinning. Remember, if you're standing on a platform and you catch a fastball, you reach your hand out, hits your hand, it'll make you rotate. So this velocity at a certain radius has angular momentum, but the full expression is mvr sine theta. If I pick a point over here, the velocity and the radius, what angle is that? I don't know. So we'd have another unknown here, 3 unknowns, theta A and theta B. But at these 2 points, like at B, we have radius here and velocity there. The angle's 90 degrees. Same here. Radius, velocity, angle's 90 degrees. So that makes this one and this one, the mass drops out, and look, we got a much simpler expression for comparing these same 4 variables. So if you're at these 2 points, highly recommended you use angular momentum. Any other points, you have to use energy, unfortunately, with all the tedious big and small numbers involved. So this is the highlight, okay? Understand how to create this expression. Basically, it's the same every time. So remember this, angular momentum at the 2 different points. Okay, the last thing, Kepler's 3 laws. I put this last deliberately. In my opinion, it's the least important in terms of not that likely that you're going to be asked questions about it on the AP. The exception being deriving this. This is pretty likely. And also, in terms of physics, it's actually obsolete. Kepler did his work in the early 1600s. Newton did his work later in the mid 1600s, I believe. Well, I don't remember the exact date. But the point is, it's important only in a historical context, in that Newton used Kepler's laws to guide his thinking and generate his theories. But Newton's theories, Newton's laws, and the energy expression and momentum that followed from Newton's laws, far superior to Kepler's 3 laws. If you're going to analyze something, a projectile sent to the moon or something like that, nobody's going to be using Kepler's laws, okay? They're the old knowledge. But the AP leaves it in the curriculum probably just for some historical context. But here they are. I didn't even write them out in complete sentences, trying to be as quick as I can. The first thing is the law of orbits. Planets follow elliptical orbits. The sun is at one focus of the ellipse. So here's an elliptical orbit. Remember from math, an ellipse has 2 foci. The sun is at one of those. Okay, so Kepler discovered that by just analyzing data of another scientist. The law of areas. Again, I didn't write it out in detail. The idea is that equal areas in equal times, just my quick way to write out. This picture illustrates what is meant by that. So let's suppose you've got this comet or something orbiting the sun. Halley's Comet again, because I don't remember off the top of my head any other comet's name, but let's say Halley's Comet, and you watch it for 1 month, okay, and it moves from here to here. Well, maybe you would need longer than 1 month to move that far. But anyways, you waited some time in it. I'll just say 1 month. And you imagine a string connecting Halley's Comet to the center of the sun, and that string would sweep out a certain area, indicated by this pink shaded here. You wait later, and you let the comet reach here, and then you watch it for 1 month again. A string connecting the comet and the sun would sweep out another area here. Those two areas are equal. Okay? Basically what this is saying in an awkward fashion is that things move faster when they get closer to the sun than when they're further away. And we have a better way of saying that through energy conservation. Okay? But it's in the curriculum. You need to technically know it. And the last thing is the law of periods, that if you square the time of any planet's orbit, it's proportional to the radius cubed. Well, that's in the circular case. This is the expression written out as an equality. Again, you need to derive this. That came earlier in this review video. So that's it. Gravitation. Okay, so again, we reviewed force. Okay, the formula, how to calculate gravitational field, how to calculate the gravitational field inside of a planet, density times volume for mass, and then you get this expression. We looked at a couple examples of the vector nature of force and field vector nature, Pythagorean theorem, or force. I had to subtract these because they're opposite directions. So the vector sum nature of those two ideas. We learned about potential energy. Technically, you need to be able to derive this. I would say that's not so important, but this is on that reference table that you get for the test. But using this is more important. We learned a little bit about space projectiles, 3 different cases: something that doesn't escape, something that escapes, and something that has more than enough to escape. And we use energy conservation in all of those analyses. Then we learned, more important, in my opinion, is about circular orbits and figuring out the orbital speed, the orbital period. Okay, so here, the period, and the energy of an orbit, okay, are all things you need to do. We looked at an example problem, very tedious, okay, so don't spend too much time with that. And then finally, elliptical orbits, 2 ways to analyze them in terms of energy conservation and angular momentum. Angular momentum only works there. And Kepler's 3 laws. So, thank you for watching, and I would say see you in the next video, but there are no more videos because at this point we have gone through the entire curriculum twice, okay? Once throughout a whole year, and again in about a couple weeks as a review. So congratulations for sticking through a very hard curriculum, a very challenging curriculum. Congratulations for learning a lot of great ideas, a lot of calculus, a lot of great mathematical techniques. And hopefully, I hope that everyone gets 5s on the AP. That would make me very happy. Would obviously make you very happy. So again, thank you for watching, and hopefully I'll see you in school sometime soon.